Hello dear students, welcome you all. In this lecture, I am going to perform the next experiment on the virtual lab, right? And the experiment that I have taken today, it is the experiment belonging to the mechanics lab that is, listed in the B.Sc first year course, right? The experiment that I am going to take up is to find out the moment of inertia of a flywheel, right? So by using virtual lab, I will find out the moment of inertia of a flywheel. So you know very well, for performing an experiment in the virtual lab, we have to go to the virtual lab. So you can see here, you can do the Google search virtual lab, then you can go to this tab virtual labs, then you will reach here. So here you can find different labs, right? From Ministry of Education under the National Mission of Education through ICT. So in these different virtual labs, you have to select mechanics virtual lab, right? When you will go to the mechanics virtual lab, you have to go to the list of experiments, right? You can see here moment of inertia of a flywheel, torque and angular moment, acceleration of flywheel. All these experiments are listed here. So I am going to the moment of inertia of a flywheel, right? And the aim of this experiment is to find out the moment of inertia of a flywheel, right? You can see here, aim of the experiment is to determine the moment of inertia of a flywheel. So first of all, students, we must know what is the flywheel, right? And what is moment of inertia. We know very well, as far as moment of inertia is concerned, that when a body has rotational motion, it possesses an inertia. That rotational inertia is known as a moment of inertia of that body. It's the ability of the body to oppose any change in its rotational motion. When it is at rest, it wants to remain at the rest. And when it comes to the motion, the rotational motion, then it wants to continue in the rotational motion. And that inertia is known as a moment of inertia or rotational inertia of a body. All the bodies that has rotational motion, they possess moment of inertia. So this moment of inertia is actually analogous to the inertia in the translational motion. We know very well then that when a body has a translational motion, it is moving along a straight line, it do possess inertia, but that is the translational inertia. And when the body is moving in a circular path, then it possesses a rotational inertia, right? So here we are going to calculate the moment of inertia of a flywheel. Now flywheel is basically an device or an arrangement that is used for controlling or maintaining the speeds inside the different engines. I'm going to show you the pics of flywheels. You can see here, this is the flywheel. You must have seen flywheel in the different machines. What is the role of this flywheel in these machines? The role of the flywheel is very clear, that the motion that we got from the engine or from a motor, that is not uniform. It can contain jerks, irregularities. So the role of the flywheel is to act as a reservoir of energy, right? When it is set into the motion, the engine set the entire assembly in the motion, this flywheel comes into motion, then it try to remain in a uniform motion due to its moment of inertia. So due to this, the power that is transmitted to the, for example, tires to the vehicle, that remains uniform. It does not contain jerks. Or even when you are using it in the another engine, any kind of engine, then the main purpose of it is to maintain the smooth motion. You can see different flywheel assemblies here. I'm showing you. You can see here, this is also a flywheel. You can see here, right? All these are flywheels. This is also a flywheel, right? You can see here different. If I show you the pic of flywheel that I am going to discuss here in this experiment, then we have to go to the virtual lab, right? So now first of all, we have to go to theory, right? We know very well, this is the peak of the, you can see here, this is the peak of the flywheel that you can see in your physics labs. This is a flywheel, right? That is mounted on the ball with, some setting, some arrangement, right? You can see here, this is the axle, right? And this is the flywheel that is mounted on this axle. The entire assembly is fitted on the wall, right? You can go through this entire theory, and this is the formula that we are going to use for calculating the moment of inertia. You can even see this formula in your practical manuals, practical books, right? I stands for moment of inertia, and m divided by n plus n 2gh upon omega square minus r square. Here I is the moment of inertia of the flywheel, n, capital N, is the number of rotations of the flywheel before it stopped, m is the mass on the string, right? N is the number of windings of the string on the axle, g is the acceleration due to gravity, right? H is the height of the bait assembly from the ground, and r is the radius of axle, right? If we want to calculate W omega, then the formula is omega is equal to 2 pi n upon t, right? We can take it average value of the angular velocity, right? So how we will perform the experiment? So I will show you that. First of all, let's do the self-evaluation. So as I told you that in every virtual lab, first of all, you have to test your knowledge regarding to that topic, right? So here we are doing the moment of inertia. So the first question is moment of momentum is called. What is moment of momentum? Moment of momentum is a angular momentum, right? Then the dimension formula of moment of inertia. Now I can show you how to calculate. We know very well moment of inertia mathematically. I is equal to mi ri square summation, right? So m, you know very well what is the dimension formula. M, r means length, so L square, T 0. T don't included here. So this is the moment of dimension formula for the moment of inertia. M L square T 0, right? M L square T 0. When the ballet dancer on a rotating table brings his stretched hand close to the chest, right? Suppose a ballet dancer is dancing on a table and he is bringing his hands. I mean, earlier he has stretched his hand, but when he has, let's take the case. Let me explain you. This is a table, rotating table on which this ballet dancer, it is performing dance, right? These are the hands, right? For understanding, let's take he is carrying some baits into these hands, right? M1, M2, right? And he is dancing on this table, and the table is rotating. So when this ballet dancer will close his hands, brings his or her hands close to the body, then what will be the effect on moment of inertia? We know very well moment of inertia depend upon the two factors, mass and distance of mass from the axis of rotation. Axis of rotation is this one, right? So when it brings hands closer, its moment of inertia r decrease, so moment of inertia also decrease, right? Very simple. So you can go here, moment of inertia will decrease. Then if the mass distribution of a given body shift toward the axis of rotation, same question, mass distribution shift toward axis of rotation, means Ri is decrease, is moment of inertia decrease, right? You have gone through all these things in your 11th class. B, consider the moment of inertia of a body when its motion is rotational, right? So submit the quiz, 5 out of 5. So all the questions are attempted correctly, right? Now I am going further, right? So to go further, now proceed. We have done the procedure, right? Yes, we are going for the procedure. So I will explain you what is the procedure. Right? Go to the simulation. I will explain the procedure here also. Right? Now this is the actual arrangement that you will found in your laboratory, right? Axle, right? Sorry, a flywheel mounted on an axle, and it has an arrangement attached with it for counting the number of rotations, right? This is the stopwatch used for recording the time. This is the meter scale for measurement of the height of this mass from the ground, right? So what you will do, you will take a string and then fasten this string, you will be given a hole here on this axle, right? First of all, you have to find out the diameter of the axle, this one, right? This axle diameter of the vehicle by using a vernier caliper, right? You can find out the diameter of the axle by using vernier caliper, but for finding out the diameter of this flywheel, because the flywheel is larger, so for that you have to take the thread, then you have measured the circumference by wrapping that thread around the this flywheel, then taking the thread down and measuring the length on the meter scale, that will be the circumference of the flywheel. So if you know the circumference 2 pi r, then you can calculate the radius of this flywheel. But as far as the radius of this or diameter of this axle is concerned, you can find it by using the vernier caliper. Right. Now this is the mass, that is we are going to place at the end, this end of this thread. So you will take a thread, place mass. We are placing a mass of 200 gram here, right? And the other end of the thread is fastened or put into the hole that is given here, and now the mass is touching the ground, right? Now what you will do, you will start rotating this flywheel. You are given a this line on the flywheel, it will help you to count the number of rotations. So you will do the rotations. When you will do the rotations, this thread will be wrapped on the axle. So here I'm doing this experiment on the earth. Mass of the flywheel is 5 kilogram. Diameter of the flywheel is, this flywheel is 10 centimeter. As I told you that it can be quite larger, so it can't be measured with the help of a vernier caliper. So you have to do the method I told you for measurement. Then mass, diameter of flywheel, mass of the ring, this ring, it is 200 gram. You can vary the mass, right? You can do 400, right? 600, 800, but I am starting with the 200, right? Then diameter of the axle, you can measure that diameter with the help of a vernier caliper, and it is 2 centimeter given here. Even you can change it, right? Now I am coming to the number of bounds. Number of bound 1, I am doing it, taking it to 5. It is your choice. Now you can see, as I wrapped this thread here by rotating this flywheel, now this mass is lifted from the ground, and the height from the ground is 10 centimeter. This is very important. This is H, right? In the formula, let me tell you, where is the formula? I'm going back to the formula. This was the formula. So in this formula, you need H also. This is 2gh. G is acceleration due to gravity. We are taking all the values here in this formula in the MKS system, SI system, right? So H is in meters. So here in this experiment, 10 centimeter, 10 by 100, 0.1 meter, right? So we have to keep the record. H is 0.1 meter. I am keeping record here. H is 0.1 meter. Mass is 200 gram. So 200 by 1000, that will give you 0.2, right? Kilogram, right? Two things are there. Now I'm going to the small n. You can see here, small n. Small n, it is the number of bindings of the string or thread on the axle. So here we have taken it as 5. Small n is equal to 5. Right. Let me write the formula here first. It is Nm upon n plus m. M upon n plus n into 2gh upon vega square minus r square. This is the formula for the moment of inertia of the flywheel. Let me check it. To nm upon n plus n, 2gh upon vega square minus r square. Right, it is correct. So as I told you, h is this one, right? H is this one. G is acceleration due to gravity, 9.8 meter per second square. W is angular velocity. We can calculate it by the formula that is given here. 4 pi capital N upon T. 4 pi capital N upon T. Capital N is the total number of revolutions that we will get when the flywheel is released. The mass is released from the flywheel, I will tell you. And T is the time taken for the flywheel to come to the rest. Small r is the radius of the axle, right? And it is here in this case. You can see here small r. Yes, radius of the axle. So in this experiment, small diameter of the axle is 2 centimeter. So radius is 1 centimeter. So in meters, it becomes small r is equal to 1 centimeter 1 upon 100 meter, that is 0.01 meter, right? So now I have all the terms except vega and capital N, right? So how we will do the experiment? So as I told you that now we have wrapped this string on the flywheel. Now what we are going to do? We are going to release the flywheel, because we have hold the flywheel by the hand, but when we will release the flywheel, now this mass that is attached here, it is at 10 centimeter above the ground. So obviously it has some potential energy, so it will start descending downward. So when it is descending downward, this flywheel will start rotating. So before this mass is getting detached from the axle, how much rotation this flywheel will take? Obviously 5. After 5 rotations, this mass will get detached. You can see here, this thread will be attached with the hole, with the screw. So when the 5 rotations are completed, this screw will be released from this axle, and this mass will come down to the ground. Now when the mass come down to the ground, right, and the screw is or that pin is detached from the axle, from very that moment you will start counting the revolutions of the flywheel, right? And you will switch on the stopwatch, right? So you will record the number of rotations that this flywheel will take after the detachment of the mass till it get stopped, and you will record the time for that entire purpose. That will give you capital N and small t that are required, capital N and t that are required for this entire calculation. Otherwise all these things we have already got. So let's start the experiment. Release the flywheel, right? You can see here the experiment started. Now the flywheel is released. It is rotating continuously. As I told you, before this mass is detached from here, it will take 5 rotations, right? So small n is equal to 5. We are measuring now the capital N, right? So wait till it get stopped. We have to wait it till it get stopped. Let's wait further. It will depend upon the friction in the flywheel, right? If the friction in the flywheel is low, it can take large number of revolutions, but if the friction is high, then it can stop shortly after it. So let's wait. Now it is stopping. Yes, yes, now it is stopped, right? So yes. So you can see here, but the value of capital N we got capital N is equal to 100.23. But here in this experiment, this simulation, it is calculating N. n is including both small n and capital N, but we know very well that small n is 5. So capital N is how much? We have to decrease, because it is calculating the all rotations, that it is starting from the from the instant when this flywheel is released. So it is counting all the rotations, so we have to subtract 5 rotations from 100. So capital N is equal to 95.23, right? So capital N is equal to 95.23. And what is the time that I got, right? It is 1 minute and 36 second. 1 minute and 36 second. 1 minute 36 seconds. So I can say it is a 60 plus 36, 96 second, right? So now I got the value of capital N, small t, right? Even in the small t, right? It has started this, stopwatch again from the instant this, flywheel is released, but we have to count the time when this mass is detached, right? So you have to make all these adjustments, because when we will see the result here, you got the result, the moment of inertia 0.0063, right? 0.0063, right? This is the value of the moment of inertia that I got. But in this calculation that are done in this simulation, this value, I think it is already taken from the instant, the value of the small t and n. They are taken as per the theory, right? So in actually, if you are doing the experiment in the lab, then you have to keep in the mind that the small t, that will be taken as the time when this mass is detached. So this is the value of the moment of inertia that I got here, 0.0063. You can see here in this, this is the this was the expression, right? So here, what will be the units of this moment of inertia? So as I told you, MI/RI square. MI is kilogram, RI is a meter square. So this moment of inertia will be kilogram meter square. Whatever we have calculated here, it will be kilogram meter square, because I is equal to MI/RI square. This is the simple way of doing it, right? So this is the way of calculating it. Now here in this simulation, I have taken these values, the mass of the flywheel 5 kilogram, this, all these things. Now you can change these values. Even you can take the number of bounds 10, or as you know, but first of all you have to reset it, right? So reset it, then you can take 3, 4, 5, what is your choice? You can change the value of the mass, you can even then calculate. So you will find the value of the moment of inertia of the flywheel in this way, right? So this is the experiment that I discussed with you here in this virtual lab. So you can do this experiment by performing it in the actual lab also, or if you don't have the actual lab, then you can perform it in the virtual lab by taking the different combinations of the different value. You can do all the calculations by yourself, and you can compare the results, whether the results we are getting, they are in agreement with these calculations, or there is some deviation, right? So this is all about it. Now after performing this experiment, you can go back to the this one, assignment part, right? So when you perform the experiment, you do this assignment, and this will help you to improve your knowledge regarding this experiment, right? So this is all about it. So thank you very much.